Okay, everything looks good on everything looks good on the slides now?
Yes, everything is good. Go ahead.
Cool, thanks. So hello, everybody. Thanks for inviting me to come and speak today. So I'm Josh Dolence. I'm a scientist at Los Alamos National Lab. I've been working on sort of topics in radiation transport and radiation hydro now for sort of a decade or so in various contexts: black hole accretion, core collapse supernovae, neutron star mergers, and so on. So today I'll be talking about incorporating radiation into relativistic fluid codes, which is a sort of slightly different prompt than I was given, but I will spend some time emphasizing Monte Carlo as a potential solution for this problem. So I hope this talk is sort of useful for everybody, but it is a huge topic, so it's hard to cover this in 25 minutes. So my apologies if I don't touch on anything that's sort of new to you. So, I wanted to at least spend just a second giving a little bit of context here. So, this slide, just to summarize it really briefly, is really just meant to convey the message that the radiation can play a lot of different kinds of roles in relativistic applications, and really that there is no one-size-fits-all solution for incorporating radiation into your fluid codes. It depends a lot on your problem, right? So, radiation can and when I say radiation, let me just be clear that I mean photons and or neutrinos. So they're both sort of relevant for the applications that people are interested in this meeting. And, radiation can play roles in sort of the thermodynamical evolution of systems. It can play roles directly in the dynamical evolution through radiation forces, and it can play essential roles in the chemical evolution. And depending on the problem that you're looking at, one or more of these may be totally crucial, or maybe all of them are totally irrelevant, in which case you can just sort of, tune out and watch YouTube videos for the next half an hour or so. So the key to getting radiation into your codes really is to understand the role that radiation plays in your problem, and then to pick the methods that sort of most affordably can serve up that sort of fidelity. Making the wrong choice here can be really quite painful. So think carefully before you move forward. So what is radiation transport? That's kind of a prompt that I put in there just so I could say that I'm not going to be talking about things like radiation diffusion, except as a limit of the full transport equation. And I'm not going to be talking about methods that are based on like two-moment closure, approximate schemes of this sort. This talk's really about full transport. So that means evolving the distribution function for the photons or the neutrinos sort of in their full six-dimensional phase space. So that's sort of most sort of elegantly and compactly written here in terms of Liouville's theorem, which just says that along trajectories in phase space, the phase space density only changes due to collisions, which is this term on the right-hand side. Can people see my mouse actually, so I can point at things?
Yes, we can see you all very clearly.
Great, perfect. So that's basically what this equation says, is that unless there's collisions, that means absorption, emission, scattering. The phase space density is just constant along trajectories in phase space. So this looks really simple. Of course, it's not. That's why I'm here talking about this. And in fact, it's really quite a horrible problem to try to solve numerically, and in fact continues to occupy whole careers and whole journals and so on. And it's been doing so for like 70 years or so. So it's a huge topic, and it's not a trivial one to get right. So why is it so hard? There's some of these points are sort of obvious and trivial. The first is that if you're trying to evolve the distribution function in a six-dimensional space, there's just a lot of degrees of freedom. And it's even worse if you're trying to evolve the neutrino distribution functions, because really you've got 6 of them. So that's six plus one dimensional problems, which is, it's just expensive. In the end of the day, there's no way around that. If you really care about evolving the full radiation field, then you're going to be paying a lot for it. The second issue relates to this convective derivative in phase space. So this is the Liouville operator. It turns out that in flat space Cartesian coordinates, this is just the familiar sort of advection operator, nice and simple, down here at the bottom. But in almost any other choice, gives rise to a fair amount of complexity in this operator. And when you go to non-trivial spacetimes, which of course is of relevance for things like neutron star mergers, this can get quite disgusting, in fact, and there's lots of issues that can arise from that. And the last issue is that transport's a uniquely horrible problem because it sort of spans a huge range of regimes, and you can think about it from, if you're more familiar with sort of fluids, imagine trying to write your MHD code. Instead of as an MHD code, you write it as a full plasma code that involves the full distribution function so that it can treat the collisionless regime appropriately, but also the MHD full collisional regime appropriately. So that's sort of the challenge. That's the analogy of doing radiation transport. It's just a non-trivial task. So I'm not going to dwell on any of these points really very long, but this is just an example of what the convective derivative can look like. So this is the 1D spherical special relativistic transport equation written in the lab frame where it looks quite reasonable, and then written in the co-moving frame where it looks quite disgusting. And the point here is just that choices can make a big difference in how complicated the expressions are for actually carrying out transport. And of course, it's not that we couldn't code this up, but it's more complicated than that, right? This is expensive. There's lots of plots involved here. And it's also, you also have to start worrying about issues of accuracy. You can imagine just doing transport in spherical coordinates, trying to model just a straight beam is actually non-trivial because there's all kinds of sort of coordinate terms that show up that are non-trivial to get right. So there's more things to worry about. So I wrote these two down because I also wanted to make another point. This is lab frame and co-moving frame, and you might ask, like, why the heck did I bother writing down the co-moving frame equation? Because it's disgusting. And it turns out it's because I left the right-hand side here completely unspecified, and the right-hand side, it turns out you really want to be working in the co-moving frame. And I'm not going to dwell on this either, but suffice it to say that that's just the natural frame to consider the interactions. The right-hand side is the interactions between the radiation field and the fluid. And that's the frame, for example, that you would most naturally consider things like equilibrium, for example. And so there's good reasons to work in the co-moving frame, but it also gives rise to a fair amount of complexity in the transport sector, right? So neither of these choices is clearly the right one. And I have this bit about Lorentz invariants. They're your friends. Use them when you can. They're not as useful as you might hope, but in Monte Carlo schemes, they turn out to be very useful. So just be aware of them. And if you don't know what I'm talking about, I don't have time to really discuss them much, but look into them. They're quite useful. Okay, so there's these issues of frames. There's actually more to this than that. I mentioned the collisionless to collisional sort of conundrum. And it turns out that developing schemes that do this, that can handle both of those extremes, is actually really tough. And in the transport literature, and in fact in other literature for numerical methods, these schemes are referred to as asymptotic preserving schemes. So you can look that up if you're interested in learning more about these things. But the basic idea is that in the appropriate limits, and in, for radiation transport, that's like the free streaming limit or the optically fixed diffusion limit. You want your numerical scheme to basically behave appropriately in those limits. You want it to give rise to a system that respects the appropriate free streaming limit, and that also gives you the diffusion limit. So why is that tough, and what does all this frame stuff have to do with it? So I mentioned that the co-moving frame is sort of the natural one to consider things like equilibrium, and in fact it's also the natural frame to think about things like diffusion, right? So we know how the radiation field should diffuse, and that expression of diffusion is written always in the co-moving frame. That's the frame in which we have a clear understanding of how this physics works. And then similarly, in the optically thin regime for free streaming, we know how to write that down trivially in the lab frame. And so this is one of those cases where you sort of have two limits that you're trying to satisfy, and they're not even in the same frame. And so there's lots of complexity that can arise from that. So many schemes that are currently in use in practice are have trouble in one or both of these limits, and all of them, almost all of them at least, rely on order V over C expansions. And I've got this in red. Beware order V over C expansions. Almost every paper you'll find on rad hydro basically begins with, hey, let's take the transport equation and expand it in order V over C, drop all the terms higher than first order, and then we're off to the races. And that's obviously not as useful for us as it is for people looking at terrestrial applications, for example. All right, so bottom line with all this, transport's complicated. The Louisville operator is terrible if you really have to just write down a discrete version of it and evolve it. The scheme that you're going to come up with, if you just take that 6 plus 1 dimensional problem and just like lay down a mesh in 6D and discretize it, is going to be really expensive and really complicated, and very well may not even satisfy all of these sorts of limits that you'd like to be able to get right. So it's complicated. So this motivates looking at sort of alternative schemes. So it's not, just directly attacking this naively with like a finite difference scheme or something, I think will likely fail for some time. So we've got to look in other directions. And one of those directions that I think is reasonably well motivated, though it's not perfect, as we'll discuss, is Monte Carlo methods. So the first, what are Monte Carlo methods? They're a large class. There's not like one Monte Carlo method. It's a large class of statistical methods that are used to solve transfer problems, but lots of other problems too. And sort of the canonical thing that always goes along with the description of Monte Carlo methods is this statement about convergence rates, which is almost always true, which says that the scheme will converge as order 1 over the square root of n, where n is the number of sort of samples in your method. And that, importantly, is independent of dimension. And why is that important? Well, this is a 6-dimensional problem. So I mentioned if you wrote down just some finite difference scheme on the 6-dimensional mesh, say you wrote down a second order scheme, which might seem quite reasonable to you. It turns out that the convergence rate for that scheme goes as the number of degrees of freedom to the -2 over the dimension. In this case, it's 6, right? So the overall convergence rate is actually n to the -1/3, which is even slower than Monte Carlo. So it's sort of a generic feature of Monte Carlo schemes is that they tend to excel in high dimensional spaces, and that's certainly true here, and is one of the advantages. All right, so if you want to picture in your head, if you're not really familiar with Monte Carlo methods, what you should picture is basically a huge swarm of particles that are flying around and interacting with the fluid. So if you picture it in a mesh or in a fluid code, you just imagine particles flying around in all different directions. Some of them, they're popping up, they're being created. Some of them are being absorbed and going away, and some of them sort of bounce off of electrons, say, they're scattering off of the fluid. And every time they interact in any of those ways, they deposit some energy and momentum in the fluid. And so, and that's sort of how they couple. So that's sort of the basic picture that you can have in your head. When it comes to Monte Carlo methods for transport, there's actually, again, a huge number of variations. By far the most popular one is so-called implicit Monte Carlo, which was introduced actually, I guess that's like 50 years now. So it's been around for a long time. There's been a lot of work on it, and it's become a pretty reliable workhorse for in a lot of application spaces. But a lot of others exist. I just picked a random set of them: symbolic implicit Monte Carlo, exponentially convergent Monte Carlo, difference Monte Carlo. They all have their own kind of advantages and disadvantages. But implicit Monte Carlo is probably a safe place at least to start if you're interested in looking at this stuff more. So one thing I wanted to mention here that I think is important, as most of us are sort of physicist developers writing codes, right? Monte Carlo methods, I think, are, I agree with this, and they're often described as being sort of close to the physics. And what does that mean exactly? It means that it's sort of, the way that the Monte Carlo samples behave is a lot like the picture that you probably have in your head about, a photon or a neutrino flying through some plasma. So, you actually, you create new samples through emission, which is, just like you think about it. They just fly on GD6 through space-time until they interact, where they may get absorbed and just go away, or they may scatter, and then, the sample actually scatters. You sample the distribution of differential cross-section, rather, to pick, how the thing scatters. So there's a lot of sort of direct analogies with the actual physics going on, and I think that helps a lot when it comes to sort of reasoning about the methods and about the issues that you might encounter. And you can contrast that with methods that, for example, rely on Jacobi-free Newton-Krylov methods or something, where the methods are so far removed from the physics that it's often difficult to really wrap your head around what exactly is going on sometimes. Okay. So now a little bit more. I'm gonna keep diving a little deeper here into sort of advantages and disadvantages. If you're looking for like a recipe, by the way, to go off and implement Monte Carlo methods or a Monte Carlo method in a fluid code, I'm not going to provide that. So hopefully you're not disappointed. We just don't have the time, and frankly, it'll be way too boring for everybody. So if you want that, there are papers that I can point you at that will give you those recipes, so you can go and do this. I'm focusing mostly on sort of the things that you should think about before one would even really attempt to go and implement a method like this. All right, so Monte Carlo methods, what are their advantages, and in particular, what are their advantages and disadvantages for sort of relativistic applications? There are two big ones, and as far as advantages go, there are two big ones, and they should not be discounted because there really are major advantages. The first is that the transport operator, I spent this time talking about the convective derivative in phase space. It turns out that becomes completely trivial in Monte Carlo methods, and because basically all it boils down to is just solving the GDP equation for each sample. So your transport becomes extremely simple to do. You just evolve a couple of ODEs for each of your samples, and by doing that, you're effectively doing transport exactly. To whatever degree you can integrate a GDP, that's the degree to which you're getting transport correct, which is fantastic. That's a really simple thing to do. It's not that expensive, except of course that this is maybe not cheap to evaluate. But if you have it lying around anyway, then it's really not terribly bad. So that's one major advantage in relativistic applications. The other one is that I mentioned this issue of frames, and one nice feature of Monte Carlo is that it's very easy to move between frames for your samples, and it also allows you to leverage Lorentz invariance in a way that's often difficult in other kinds of discrimination schemes. So this is a great advantage when you're doing things like scattering, right? You can, for example, boost into the rest frame or boost into the frame of the electron that you're going to scatter off of, right? And then to directly sample the differential cross section to scatter the thing and then boost back into the lab frame. And that sort of accounts for everything that you would try to account for otherwise in more complicated ways in other schemes. And it's fully relativistic and essentially exact. So there's really some strong advantages there. One thing I don't list here, but that's worth mentioning also is in relativistic applications, we're sort of used to being limited by the speed of light. And in a lot of applications for radiation hydro, like terrestrial applications, speed of light is really fast. And for us, it's kind of, normal. And it has a great advantage because the transport itself, forget about coupling or anything, the actual transport, moving radiation in space-time is sort of reasonably considered to be sort of explicit, local, right? You can only move like from one cell to the next cell, not from one cell to some cell on the opposite side of the domain. And that's a huge advantage because it really simplifies a lot of the sort of machinery that you require in your code to handle these particles moving around and so on. Okay, so those are huge advantages. There's disadvantages also, and by the way, I'll come back and describe some more subtle advantages in a minute here. So disadvantages, though, at a high level, there's noise. The schemes struggle at high optical depths. They don't really deal with stiffness very well. So stiffness, in other words, stiffness is if there's a time scale for like absorption and re-emission that's very fast relative to the other time scales in your problem, Monte Carlo methods can struggle sometimes to deal with that. If you've got significant radiation pressures in your problem, like give up now and move on because this is probably not the method for you. And I'll describe why that is in the next slide. And then the last one's kind of a practical thing, which is just that a lot of times how this goes is you have a fluid code and you want to add radiation, and so particles come in kind of as an afterthought, and that can be an issue just from a practical perspective. All right, so let's see, I've got 5 minutes or so. So let me speed up a little. Monte Carlo skeletons. So there's issues with Monte Carlo. This one's important, so I wanted to make sure I mentioned it. Monte Carlo methods are actually not asymptotic preserving. And so a good example of that is you imagine a setup where you've got sort of a big domain. In the middle of it, you've got a wall that's one cell thick and has infinite optical depth. And then you irradiate it from one side. And you ask the question, like, what's the radiation field on the other side? The answer should be 0, of course, because you've got infinite optical depth. But what happens in practice is that you irradiate it from one side, a photon or a neutrino comes in, gets absorbed on one side of the wall, and you should heat up a layer on this cell that's like sort of epsilon thickness. But what happens in fact is that you heat up the cell, the whole cell, and then that cell can radiate, and it can radiate from anywhere in the cell, and so it radiates out the other side, and so you get this error that people refer to as teleportation error. And so that turns out to break its asymptotic preservation. It doesn't actually obey the diffusion limit appropriately, which can be a serious issue. It emits unphysical solutions. You can get overshoots in temperature, and this is based on time steps, and it really relates to the fact that you've split the emission and absorption into sort of separate processes, and so that can violate so-called maximum principles. This is the bit about radiation force. So it turns out that in optically thick environments, when you try to calculate things like the first moment, like the flux or the radiation force, you end up being incredibly noisy because the effective fraction of samples that go into that calculation is dramatically reduced. It's something like F over CE, which is much less than 1. And so your radiation forces are complete garbage when it's optically thick. And this is one reason why going for a radiation pressure dominated kind of problem with Monte Carlo is a bit dangerous. And the last thing is that in optically thick environments, the efficiency of these schemes drops ridiculously fast. So you end up doing this kind of thing where a sample can bounce around forever in a cell, not actually doing anything of significance, but taking up a lot of cycles. Okay, so as far as strengths go, it's relatively straightforward to implement, and you get full transport out of it, not diffusion or M1 or any of these approximations. It turns out that we don't always actually really need a highly accurate representation of the radiation field everywhere, and there's good reasons for that. And Monte Carlo sort of naturally accounts for that. And I'm not going to be able to go through all these reasons, but we can come back in the questions if you're interested in these. Free streaming, it gets sort of for free and basically perfectly. And then overall costs can be much lower than for deterministic methods. But again, it depends a lot on your problem because there's issues with high optical depths and so on. Okay, so advanced topics, and I'm really going to zip through these because of the time. There are, like I said, there's been like 70 years of work on Monte Carlo. It goes back to like the 50s. There's a lot out there, and these are sort of broad brushstroke kind of categories of things that you might look into. Variance reduction techniques is basically what can I do to reduce my error at a fixed number of samples, and there's lots of methods out there that help you do this. Particle splitting, Russian roulette, biasing, these are just words, but these are things you can look into. There are techniques to improve the efficiency of the codes in diffusive regimes. So discrete diffusion Monte Carlo is one, random walk acceleration, there's some papers and that sort of stuff. There's some schemes that help you deal with stiff inelastic scattering, but this is actually still a problem. No one really has a great scheme for dealing with this sort of issue. So there's lots of stuff out there to look into that might help, at least help, but not completely remove some of those deficiencies that I discussed. There's existence proofs. I'm not going to have time to go into these codes at all, but there are at least 2 open source full transport GR MHD codes out there. Blight is one, and New Blight is the other. They're both based on GR MHD as implemented in HARM, or at least it's a HARM derivative, so it's evolved from the original HARM code. I think it's different than like Scott's HARM 3D code, for example. Transport derives in both cases from GR Monte, which is a Monte Carlo transport code I wrote back in grad school. This one includes various kinds of physics, and you can look into this. And New Blight is the code that does all the same things, but it also adds general EOS, and it deals with neutrino transport instead of photon transport. So we've been looking at post-merger disks and collapsars, for example, with that. So you can go check those codes out if you like. This I really have to fly through now because I've got like a minute left. Monte Carlo's pitfalls and overcoming them. So my postdoc, Ben Ryan, and I, who's actually now staff at the lab, worked out a new scheme we call method characteristics moment closure. And I'm not going to be able to describe it really, except to say that we designed this scheme to try to retain as many of the benefits of Monte Carlo schemes as we could, but get around some of its major shortcomings. And our goal with this was really to get to the point where we could model things like super Eddington accretion flows, radiation pressure dominated kinds of flows in relativistic environments, stably and accurately with full transport. And I think we basically achieved that, and we've got a paper that describes the methods. Here's various kinds of test problems, and there are lots of features of the scheme that are worth discussing more. But I'll sort of leave it here. People can ask questions or just look the paper up if they want more details. But there are alternatives to Monte Carlo out there that I think are quite promising. So I'll put the conclusions up. I'm like 9 seconds over, so I'll sort of leave it there. But I do want to mention one thing before I let go, which is totally unrelated to this talk, but I saw it on one of the documents. I haven't been able to make it for the last 2 days of the meeting. But I did see the documents. There was some discussion of Athena++ and discussions of GPUs and Cocos and so on. So I wanted to point out this open source code Parthenon that we're working on in a collaboration between Los Alamos, MSU, and with Jim Stone, actually. What this is basically the AMR infrastructure from Athena++ that's been separated from the physics. And we've introduced Cocos for performance portability. So it is not fully baked yet, but it's well on its way to becoming a performance portable sort of generic multiphysics AMR code that you can build things on. And there are, in fact, right now is a grMHD code that's being developed on Parthenon. So we certainly had that sort of stuff in mind. And I'll leave it there. Now I'm over time.
Wonderful. Thank you for this beautiful talk. Jeremy Schnickman will be chairing from now on, so he's taking the questions for you.
Hi.
Thanks.
Hi, guys. Hi, Josh. That was great. Thank you so much. Okay, so I guess you can let me pull up the participant list. We can see some hands raised. Okay, Manuela, do I need to explicitly unmute people, or can people unmute themselves?
No, they can unmute themselves. You just pick who you want
Okay.
to ask the question.
Okay, so Julian's hand was up first. Julian, why don't you ask your question?
Okay, well, Josh, a very interesting talk, remarkable overview. And I read the preprint of the moment-based Monte Carlo. It's great interest when it appeared. It was missing one interesting characterization, which is how much cost does it add to the fluid side?
So if you're asking how much more expensive it is to run a full rad hydro calculation or rad MHD calculation than an MHD calculation, the answer is that it depends. It's certainly more expensive. It's hard to give you an exact number, but in order of magnitude, it's not unreasonable. When you think about the fact that you're solving, the number of degrees of freedom really has completely skyrocketed, right? You're evolving a much bigger system.
Yeah, I know the numbers for the Athena version of radiation transfer,
okay.
The time-dependent version. So I'm curious how this compares.
So there's a difference, though, which is that the Athena version is gray.
Yeah. Right.
So it's not really evolving the full 6-dimensional phase space. So if you did multi-frequency transport in the Athena version, you'd run into it'd be however many frequencies you had times more expensive, right?
Yeah.
So one of the major advantages that I didn't get to talk about in the scheme that we've developed is that all of the samples that we push around, that we still have particles that fly around, as you know, all of them carry with them a full spectrum of the radiation field. And what that does is it makes frequency-dependent transport and gray transport almost the same cost, because the transport operator itself doesn't cost anymore when you go to multi-group transport, which is a huge advantage of this sort of scheme when it comes to expense. So roughly I'd say about an order of magnitude more expensive, but again, it depends a lot on your problem.
Well, that would beat the Athena version, which is something like 50 to 100 times slower.
Yeah, I don't think it's quite that bad, actually.
All right, thanks. Next up, I think is Zvi. And Julian, in the participant list, just click on your hand again so that it doesn't look like it's still raised. Thanks. Okay, Zvi.
Hi, my question should have probably been slightly before Julian's, because I was wondering if you can just say 2 or 3 sentences about what's the basic difference with what is the basic characterization of this method that you just mentioned, this moments Monte Carlo.
Yeah, so a brief summary of it would be that the method is no longer stochastic. It's really a deterministic method. but we still rely on particles to represent the full radiation field. And we use the full radiation field to basically close a gray moment system, but do so essentially exactly, right? So we get the moments that we need to close the moment system, and also the appropriately averaged opacities, for example. So that's the basic idea. There's still noise in the scheme because we use reconstructions of the particles in each cell to represent the full phase space distribution function in each cell, and that reconstruction process actually introduces noise, and so that's basically the description.
Thank you. One quick question from David. David, we can't hear you. I think you need to unmute yourself.
Sorry, can you hear me now?
Yeah.
Yes.
Oh, okay. And you mentioned very briefly implicit diffusion Monte Carlo and other schemes that treat the high optical depth problem in Monte Carlo schemes. One issue in relativity is that the diffusion equation is not a well-posed equation. And I know that instead, most of the Newtonian methods, they basically fall back to the diffusion equation.
Yep.
So how does it work for a relativistic problem?
That is a great question, and one that I've had ever since I first was introduced to discrete diffusion. I don't know the answer. I'm not sure that anyone's actually sort of successfully formulated the equivalent for a relativistic, in a relativistic kind of formalism. You know,
so all
I
of these
think
methods are still Newtonian.
What's that?
All of these methods are still Newtonian then?
Yeah, discrete diffusion methods, the ones that I've seen certainly are still Newtonian. I actually don't think it's impossible. There's more discussion we could have. I don't think it's impossible to formulate something that looks like this, but it's certainly not as trivial to do so.
Okay, thank you.
Thanks. I'm going to put this down as a discussion point for this afternoon, maybe having a bunch of these radiation transport groups, see if we can come up with some kind of standard community test problems to get these in the relativistic case. Might be helpful. So get compare these codes, get other people involved. Okay, great. So Josh, you'll stop sharing your screen and we'll switch over to